Transmission of information is the main motive of computer networks. This requires bandwidth for transmission. Active and smart use of bandwidth can be a big challenge to electromagnetic communication. Multiplexing is one such technique which allows multiple transmission sources to share a larger bandwidth. So basically, multiplexing requires the better utilization of the bandwidth, and that is a big challenge because bandwidth has a cost involved, and when the cost is involved we need to manage that particular thing with efficiency. So that is why multiplexing is required, and it is a technique which allows the multiple transmission source to share the larger bandwidth, because the bandwidth is there, and if we are not sharing it, it cannot be used with the efficiency. So that is why multiplexing is required. Now let us discuss multiplexing and its types. When two devices are connected by a point-to-point link, it is generally needed to have multiple frames outstanding so that the data link does not become a bottleneck between the stations. In contrast, it may happen that two communication stations will not use the full capacity of data link. So in such cases, the whole capacity can be shared for better productivity. A basic term for such sharing is called multiplexing. There are basic three types of multiplexing. Frequency division multiplexing, where the frequencies are divided. Wavelength division multiplexing, where the wavelength is divided. And time division multiplexing, where the time is divided. So one basic example of multiplexing is long-haul communication. Trunks on long-haul network are high-capacity fiber, coaxial or microwave links. Using the multiplexing, these links can carry large number of voice data or data transmission simultaneously. So data and voice can be transmitted simultaneously in the long-haul communication, and that is done by the multiplexing. In the further slides, we are going to discuss these types of multiplexing in detail, like frequency division multiplexing, followed by the wavelength division multiplexing, and then the time division multiplexing. As shown in the figure below, multiplexer is combining data from n input channels and transmits over a higher capacity data link. Demultiplexing accepts those combined or multiplexed data and splits them into according to the channels and delivers the data to the proper output lines. Below figure shows a multiplexer. In the simple form, there are n inputs and n outputs. We can see that in the figure, and the multiplexer is directly connected to the demultiplexer using a single data link. This link can carry n separate channels of the data. Here we can see there is MUX and DMUX. MUX stands for multiplexing and DMUX stands for multiplexing, demultiplexing. So multiplexing is the incoming n inputs are coming, and then multiplexing is transferring them into one and n channels, one link and n channels, and then demultiplexing is giving again it to the n outputs. So there is a process of multiplexing and demultiplexing. So it's a concept of multiplexing. Now let us discuss the frequency division multiplexing, FDM. By now we know the multiplexing is a method of sharing the bandwidth. Why it is required, we all understand, because we have seen that the bandwidth needs to be bifurcated and it is to be divided in the channels, and then because the bandwidth needs to be shared, the channel needs to be shared. So FDM is a method of sharing the bandwidth of a communication channel among multiple users by frequency translating. It is an analog technique. When the bandwidth of the link is greater than the combined bandwidth of the signal to be transmitted, then we use FDM. We can see in this statement that the bandwidth of the link should be greater than the combined bandwidth of the signal. That means the bandwidth of the signal must be lesser than the bandwidth of the link. then we are using the FDM, right? There is a requirement of using the FDM in that case. So if in each signal is modulated onto a different carrier frequency and the carrier frequency are sufficiently separated so that the bandwidth of a signal do not significantly overlap, then more number of signals can be carried at any time instance t. In this diagram, we can see the frequency division multiplexing is depicted, where there are multiple channels and which are divided. The bandwidth is divided in multiple frequency channels. A very well-known example of FDM is broadcast and cable television, where the frequencies of the channel is divided and bandwidth is divided in frequencies. We can see 6 signals are fed into the multiplexer over here in this diagram. This multiplexer modulates each signal onto different frequencies, F1 to F6, using some carrier frequencies. These carrier frequencies are separated by adequate bandwidth to accommodate the modulated signal called the channel. So modulated signal is called a channel. These channels are separated by the guard band. What is guard band? It is being used to divide the channel so that the channels cannot interference with each other, should not interfere with each other. Otherwise, it will create the noise and it will create the distortion. So to keep the frequencies separate or the channels separate, we need to use the guard bands. We can see over here the lines in between the frequencies are depicting the guard bands. Now let us discuss the next multiplexing type, which is wavelength division multiplexing. So it is conceptually similar to the frequency division multiplexing. Only difference is it is purposefully designed for fiber optic cable to support the high data rate. Because we all know fiber optic cable communicate the light signals, and so that is why it supports the high data rate. Like FDM, it is also combined different signals of different frequencies, but the frequencies are very high over there. So for WDM, rather than a signal, multiple light source need to be combined as well as a split. That can be easily done by the prism. SONET network is one of the application of WDM. There, multiple optical fiber lines are multiplexed and demultiplexed. That we are going to discuss later, SONET. Here we can see the wavelength division multiplexing, where the wavelength are divided and then it is being combined and then again it is being divided. So multiple wavelengths are being combined and then it is being transmitted. Lambda 1, lambda 2, lambda 3 we can see in the diagram, and then when it is reaching to the destination, it is being bifurcated once again to lambda 1, lambda 2 and lambda 3. Now the next multiplexing type is time division multiplexing. We have seen in the previous section that FDM is used in normal wire, or we can call it as a twisted pair or coaxial cable, and WDM is specially designed for the optical fibers. So time division multiplexing can combine various digital signals onto a single transmission media. It is a digital process to share the high bandwidth of link. It allows more than one connections. It share time rather than the sharing of a portion of a bandwidth like FDM. In the FDM, we are sharing the portion of the channel or the bandwidth, but here what we are doing is we are dividing the time so that one signal can be transmitted separately to the another signal, and they are not being transmitted simultaneously time to time, right? So they can be transmitted likewise. So we can see in the figure below, there are 6 inputs. Here all the signals can be carried on a single transmission path by interleaving portion of each signal in time. Sometimes it can be bitwise or blockwise. So it is being shown in this figure. We can see over here the channel 1 to channel number 5 are there, and then we are dividing it into the based on time we are dividing, and frequencies are not being divided. So there are two type of time division multiplexing. One is synchronous, another is statistical. In synchronous TDM, the data flow of each input connection is divided into the units and time into some fixed slots. So each unit occupies one input time slot. Statistical TDM multiplexing is a method of transmitting multiple types of data simultaneously across a transmission cable or line. STDM is commonly used to manage data transmission over a local area network, or we can call it as a LAN, or remote area network. We call it as a WAN. So the basic difference between the synchronous TDM and statistical TDM is pre-assignment of the time slot. Unlike synchronous TDM, time slots are not pre-assigned in statistical TDM. Here, user data are buffered and then transmitted with a new time slot. Hence, the statistical TDM is more efficient than the synchronous TDM.